Topic 7 deals with recursion. And recursion is a challenging topic. Before we get to Dr. Peruli's materials, I wanted to discuss a few things with you related to the idea of recursion that I'm hoping will help you understand it a little bit better. I wasn't sure whether to make a bunch of short videos or just to do one intro, so if you feel like you're struggling later on, maybe come back to this video and review some of the ideas that I talk about here. It might make more sense after you've seen some examples. In the Purdue course, we actually don't address recursion until the end of the course, topic 15. Here we decided to move it up because we just talked about methods, and frankly it's a little bit more important to the AP course than it is to the Purdue course. Because of that, the first video that Dr. Peruli makes references something called a linked list node, because she's talking about an advanced data structure. And there's another topic that we're going to deal with which has advanced data structures in it, and so that's why that comes up. You can ignore that for now, and I promise that when we get to the data structures topic, you can go and watch those videos and you'll understand a lot better. So let's talk about the idea of recursion from a conceptual standpoint. When we want to kind of discuss what it actually means to write a recursive function, what we're doing is we're basically establishing a segment of code that will repeat a set of instructions until it reaches some basis case, some simple case. It sort of might remind those of you who like math of proof by induction, because there's always that one base idea and then the inductive steps. Essentially what you're going to do is you're going to create a series of functions where a function call exists within the definition of that function, and that function call is a function call to itself. So it's almost like self-referencing. And what that does is it basically breaks the execution at that point and restarts the function at the top. But you might be thinking, well, that seems like that would create an infinite situation. Well, we have certain conditional clauses in place so that it doesn't go on forever. So the point is, at its most basic, you could rewrite pretty much any loop you can think of using recursion, as long as you can define it using a recursive process with a base case and a recursive case. Okay. Now, why would you do this? A positive, a lot of people think recursion is very elegant, that it takes a very special kind of thinker in order to actually think recursively. So you'll get lauded for your beautiful solution. The con is it might run more slowly, and we're going to talk about why real briefly here. The stack. And I say the stack, but I should start by just saying a stack, which is a data structure. It's a last in, first out data structure, meaning that the last item that is placed into the data structure will be the first one out. And the stack and a queue data structure are two data structures that actually have a rule about how information can be taken in or taken out and put back in. The way to think about this is like washing the dishes. If you're the first person to finish at the dinner table, your plate is at the bottom of the stack. It's the first one in, but it'll be the last one out. Okay. Meanwhile, your kid brother takes forever to eat. He puts his plate on top. His is the last one that goes on the stack, but it'll be the first one that comes out. When you put a dish in the sink to wash it, you're pushing that dish on the stack. When you remove a dish from the sink, you pop it off the stack. Those are the verbs that we use with stacks. Okay. This is a data structure that you could use in programming if you wanted, but the reason we brought it up here is because of something called the call stack. Call stack is an abstraction, and really what it is it's a memory management tool that stores the state of the program at the time of the method call someplace in memory, so that when you return from that method call, when you finish all the instructions in that method call, you can fetch out that memory, all the data that you had, so that your program can execute just like normal. So like if I had some local variables that I had created inside a method, and then I called a second method from inside that method, it would save all those local variables, so that when I returned from the method call, when the flow of control came back to the original method call, I could get those variables back and I could use those again. The reason why it's important to talk about the call stack even though it is an abstraction, something that you don't necessarily have to know about that happens behind the scenes as you program and run your code, is that it requires time to move things in and out of memory. And you probably can imagine that. Anytime you've had lots of programs open and you've flipped from one window to the other and suddenly your computer slows down, that's sort of what's going on behind the scenes, is that memory is being moved around and you got to get the instructions for the new program. That's what we refer to as overhead, meaning there's an overhead cost to actually using recursion. Okay, and if you have a recursive function that goes 20, 30 layers deep, it keeps calling itself over and over again because it hasn't reached the basis case, you develop a lot of overhead. And that can sometimes even cause your program to break. You may sometimes see an error in Java that says that you've exceeded the call stack. So why would you use something that could break like this? Well, some problems can only be solved using the concept of recursion, and I'll give some kind of conceptual examples. First thing to do is think of a tree with branches. A tree is actually a data structure that we use commonly in Java, but I picked this as an example because I think it helps you to visualize what recursion sort of looks like. So let's say I have a tree. Think about like the tree outside your window. Let's say the trunk of the tree comes up and there are 3 branches. Okay, and those 3 branches then branch off themselves. Okay, let's say the leftmost branch also has 3 branches. If I look at that leftmost branch by itself, it kind of resembles the original tree. And that's sort of the idea of recursion, is that you have like a smaller problem. It's almost like breaking things into smaller problems until you reach the smallest possible problem. Okay, so we can explore each branch as a subtree. Maybe an example that's less abstract that you'll understand a little better, especially if you like games like chess. I know a lot of people who have an affinity for programming also have an affinity for chess. Programs that have been written to play chess sometimes use what's called a look ahead. So that way when they decide to make a move, they weigh the values of each move based on what are the outcomes that could happen from that move. And of course those algorithms are complicated, but the look ahead part isn't. So essentially what you do is you save the state of the board and you make your move, and then you trace out possibilities that could come from that. What would happen with other moves happening, and really good computers that can handle lots of memory in the call stack can look ahead lots and lots of moves, and then backtrack when those moves don't work out, evaluating all the way. Another kind of look ahead mechanism can happen if you're trying to solve a maze, and you'll see a great example that Dr. Perulli will run where that's exactly what she does. Explore those avenues that may or may not work. Once you decide they don't work, come back to the original position and keep going. Why is this important for the AP exam if you plan on taking the AP exam? Well, there are 2 algorithms we're going to talk about later in the course called binary search and merge sort, and those get discussed in some detail in the AP course, and you need to understand how they work. So those are both recursive solutions, and we'll talk about recursion at that time. The other thing is that on the multiple choice section there are not a lot, but probably about 2 or 3 questions on every exam that talk about recursion. They give you a function definition and an initial input and then ask you to solve for that input. And so you have to be able to trace through a recursive function, so you need to know how that works.